we intend to go from the special to the general to the universal, in that direction. So, okay, special theory of relativity. So, early years of 20th century, I mean, what happened? So let's do this as an interactive thing. So, why did we need special relativity? I mean, everything seemed fine, and then why Einstein had to propose this theory? So there were certain experiments, right? So the main feedback, the main impetus came from experiments, and of course a great success of Maxwell's electrodynamics. So these were the two aspects of the physics prevalent then that led to special relativity. So anyway, so I'll just summarize the basic idea and basic theme of special relativity in a couple of slides. So what we are doing in special relativity is looking at the world, at the universe, as a conglomeration of events, which is what we do in science anyway, in physics anyway. So we are interested in certain things happening at a certain point in space and a certain point in time. And then we try to look at causal connections between events, like why things are the way they are. So that's science. And so that's very basic. So there are events, and we describe events as coordinates, and this is what is the main thing. We describe it, and we believe that it is describable as a set of coordinates in space-time with one time coordinate and three spatial coordinates. So that's very basic. To put these labels on events, so events are just like, you know, the tossing of a coin, or me giving a talk, or, you know, anything, or light signal traveling from one point to another. So, everything comprises this set of events. The fact that we can associate coordinate labels, or like associate a quadruplet of numbers to each event, it's not trivial. And the fact that you can do it implies that you have to have what is called a reference frame to do this, right? So you need a frame of reference, and in special relativity, we are interested in a special kind of frames. What are these frames? So what is an inertial frame? So it is like a conundrum. I mean, Newton gave a first law, which is supposed to be a law which is true in inertial frame, but then it's basically the definition of the inertial frame. So it goes around in circles in a way. But basically what we have is a definition of a certain kind of frames, which are, as you know, gross idealizations, right? Because you never really have an inertial frame. Why? Can anyone tell me why we cannot have really an ideal inertial frame? Right, so the only situation where you can probably have it if the universe didn't have anything, just vacuum. It's just absolutely trivial universe with nothing. That would be like a global inertial frame. However, it turns out that the laws of relativity, laws of special relativity are indeed correct, and indeed correct on certain scales, certain energy scales. So there must be something true of inertial frames as well. They must be not too bad. I mean, must be existing to some approximation these frames. So we shall come to that. And you know what is this approximation? Where can we safely say that this is an inertial frame? Yeah. So basically, what it boils down to is the fact that you can probably have an inertial frame in a very small region of space-time. I mean, a small region of space-time, you can probably ignore the effect of all force fields, including gravity, but that can only be done in a... So how do you intend to do that? So if there is some mass, I mean, if there's any energy, there would be gravity, right? It's not like electric field, which can be shielded off as such. So how would you ensure that you have an inertial frame, even in a very small region of space-time? I mean, it's again an approximation. So you can say that in a very small region of space-time, for example, you can imagine this classic example of sitting in a falling lift and thereby feeling weightless. So you have locally in a very small region annulled the effect of gravity and become weightless, and in a freely falling frame, you can possibly use the laws of special relativity. But again, that assumes that the gravitational field is constant, it's not changing across the length of the lift, so there are approximations involved. So this is a gross idealization. and thereby special relativity. It's very special. Alright, so the way things work is that you first define your events. So all of physics is a conglomeration of events and causal connection between events. So you first have to identify your events. Then you set up your frame. In this case, an inertial reference frame. So let's assume they exist. In special relativity, let's make a conjecture that they exist. And this frame describes events as in the space-time by coordinate labels. That's the first step. You associate coordinate labels to events. And then, of course, there is nothing unique about one coordinate frame. So that same set of events can be described by another set of quadruplet, another set of 4 numbers, which would amount to a transformation of frames, transformation of coordinates. So you should be able to label events by coordinates, and also you should be able to describe the same set of events in different coordinate systems, and you should know how to do this. So that describes your space-time. All right. Next question is, well, that's space-time. What about physics? What about the rest of science? So what happens is, now on this space-time, on this background space-time, you have fields, matter fields. So you have electric field, magnetic field, or temperature, whatever, everything that you know. So they are residing on what is called mathematically a manifold, and on this structure you have various fields. And the whole philosophy of mechanics is to consider various force fields and trajectories of test particles in force fields, right? That is what we do in physics. So now these trajectories in Newtonian mechanics, if you remember, which was the mechanics which people used to do before Einstein gave special relativity, was that you had r as a function of time. This was the question, to find r as a function of time. So you had a time which was kept aside, and you had these 3 coordinates x, y, z, which you are supposed to find as a function of time. Now this scheme gave this time a very unique place, because we are looking at about everything evolving in time. So they are intrinsically different from x, y, z, right? And so you have x, y, z and time. So time is here, and then you have x, y, z. This is the Newtonian or Galilean picture. Is that t in the blind zone? Okay, so this is the coordinate and this is the time, and they are different. And of course, the same question as to what these numbers would be in different reference frames was asked in Newtonian physics as well. But what was the big difference? The big difference was this was never considered something that would transform between 2 coordinate systems. So time was universal, it was just out there, it's always the same in every coordinate system. So you would never believe that just hopping into a new coordinate system would change your time. But these would change, and thereby velocities would change as you go from one frame to another, and you would have transformation of velocities and things like that. That was the Galilean picture. And this is abandoned. And all of you know special relativity, so I'm just summarizing it. So this idea was abandoned because now you have x, y, z and t simultaneously forming a quadruplet defining an event. And we are now not interested in r as a function of t, but this entire event changing along a world line. That is the new picture. So we have to define what is called a world line, which is basically the evolution of an event in space-time. Right? So that is the trajectory in space-time now. And since now we have put everything together in a quadruplet, they would all transform when you go from one coordinate system to another. And in the most general case, they would mix up with each other. The transformation of x, y, and z will involve time, and this will have this, and all sorts of bizarre, counterintuitive phenomena occurs because of that. Alright, so this is the basic thing. So events are labeled, as I said, by 4 numbers. We write it collectively as x mu, And then we have, so let me just go back one slide. The most important thing is bullet number 4, which are the two postulates of relativity. And the first of it is principle of relativity, which says that laws of physics should not depend on the frame you choose, because the events are there, out there, they are physically real, but your coordinate system is an artifact. You are choosing a coordinate system to describe events, right? It's your choice. So when you choose something, you could choose something else, and you have that freedom. But the laws of physics, which connects events through causality, should not depend on your choice of coordinates. So that's like a belief we have. That makes sense. So that was a belief which was prevalent even during the time of Einstein, Galileo's principle of relativity. But what Einstein did was incorporated this experimental result that there exists this velocity of light, which is a universal constant. It does not change when you go from, it's a velocity, but it's a velocity which does not add like velocity of a boat when you are going down the stream or up the stream, or like sound waves. So it's a very special kind of velocity in some sense. And you know that greatest null experiment. What was that? The null experiment, which the Michelson-Morley experiment, of course. And these two ideas, if you read Landau-Lifshitz, basically these two statements, if I say, which we call the two postulates of relativity, actually can be mathematically articulated. The exact mathematical articulation of those two statements together is the fact that there exists a quantity called the interval between two events now. So you have a reference frame and you have two infinitesimally separated events, and you define an interval between those events by this formula. Look at the presence of a negative sign. Had this all been positive, it would just be the normal distance between the 2 points, right? Pythagorean distance. But this is not really a Pythagorean distance. It's some kind of a distance measure because it's a quadratic form, but not quite Pythagorean though, not quite Euclidean. It's called Minkowskian actually. And this is a quantity which is an invariant. So this term we use all the time in relativity, invariance. Invariance means things that don't change. So you can calculate this particular number in any frame for those two events, right? But the interval will remain the same. Individual points will be labeled by two different set of 4 numbers, but when you calculate this object, this shall remain the same. And that actually follows from the two postulates of relativity. It can be actually shown that this is the mathematical statement of the postulates of relativity. Okay, so we write it in a compact form by introducing Einstein's summation convention. So this ds square equals to eta mu nu. So wherever you have a repeated index, it implies a summation. This you should get used to. So there is a sum over mu and nu, and this mu nu of course runs over space and time, t, x, y, z, and this eta is a diagonal matrix 1 minus 1 minus 1. Just writing the same expression in a compact notation. But just that we have introduced a 4 by 4 matrix eta in the process. And what this eta does, it tells us how to calculate an invariant distance or an interval in space-time, right? So if we were living in a world where there was no special relativity, but Euclidean physics was good enough, and the space was 3-dimensional instead of 4, so you would have just x, y, z. So you know that, for example, if you take 2 points, that the length of a vector, 2 points which we can join them by like a vector, so you know the length of the vector remains invariant when you make a coordinate transformation, right? And the length of the vector is just dx square plus dy square plus dz square, right? But that's Euclidean. It turns out that when you have space-time, instead of the Euclidean distance, it's a 4-dimensional Minkowski interval that's an invariant. And this is the crux. This is a very important idea in special relativity. So what does it actually mean? It means that if you have a set of numbers, x mu, defining, like labeling an event, and the same event is described by x prime mu in a different frame, then they are related by a transformation. That's what it means. Same point being labeled by two sets of coordinate labels. So that means basically there's a transformation between them. And the transformation is written as a matrix now, lambda. It's a four-dimensional column vector, x prime, a four-dimensional column vector x, lambda would be a 4 by 4 matrix. Right? So it's written in a matrix notation. Now if I say that the postulates of relativity means, it ensures that the interval is the same despite the transformation of the individual coordinates, then you can just calculate the interval in the primed frame and equate it with the interval in the unprimed frame, and what it turns out is that you get this property, lambda transpose eta lambda equals to eta. Right? Do you remember rotations? If you have a vector which is rotated by some angle, right, and you have the components of the vector, say ax, ay, and az, and you rotate the vector by some angle theta, so ax, ay, az will of course transform. Right? What is the transformation matrix? Anybody remembers? Angle theta at this rotation about z-axis. Cos theta sinus sin theta 0, minus sin theta cos theta 0, 0, 0, 1. Right? That's the transformation matrix. What is the most important property of that matrix? It's an orthogonal matrix. An orthogonal matrices have the property, if you call the matrix R transpose R equals to identity. But here you see, this eta is not identity matrix. What would make eta identity? If you have, instead of minus 1, if you have plus 1s. Right? So this is basically what is called a pseudo-orthogonal rotation. It's like, it looks like some sort of a rotation, but if eta was just identity matrix, then it would just be your rotations, normal rotations in 4D. Then you have lambda transpose lambda equals to identity. But it's not identity, the eta sits there. And this eta is not the identity matrix. And this, so a set of transformations which follows this are what are called Lorentz transformations. And this is a set of transformations which goes from one frame to another, keeping the invariant interval intact. Right? Just revision. So some examples. So for example, you can just have simple rotations. You might not just want to touch the time, keep t prime equals to t, and just do a rotation, spatial rotation, do something in the spatial part. So that would again be a part of this set of Lorentz transformations. And of course you have boosts. What are boosts? It's a velocity given in a, so you have a frame which is moving with respect to another frame by, there's a relative velocity between them. And so if v, this capital V is the relative velocity between the two frames, then the standard form of Lorentz transformation. And you see the t and the x actually mixes up. We are using a set of the units where c is 1. Okay, c is not there. And of course, if you know how velocity, how the coordinates transforms, you can immediately write down how the velocities transform. So you can write down the velocity transformation. Now, since time transforms and space and time gets mixed up in these transformations, you have all these rather, bizarre effects of special relativity which you don't see in your Euclidean day-to-day life. So, of course, there is, some of these are relativity of simultaneity. So two events, if they're simultaneous in one frame, may not be simultaneous in another frame. Right? So the idea of, because the moment you know that there is no global time, no absolute time, I mean, everything that is related to temporal separation will get jumbled up when you transform between frames. So, and all these three are essentially the effects of that. I'll just not go into details of these because you want to go into GR. Now, something very important. Important is when you see that the time is something which is transforming. However, there is, I mean, for example, there is a neutrino of some unstable particle, say a muon, which is decaying. Right, and muon is decaying into some other particles. Now, can you make a statement about the lifetime of decay? Or like I say that between these two things there is a time scale which is, say, this order of 5 seconds. Can you actually make such statements? I mean, it makes no sense anymore, right? Because everything will depend on the frame you're using. So that would depend, you have to again specify this is with respect to a frame which is moving with such and such velocity with respect to this. So it is all messed up. So you can't really talk about time scales as such. Right? However, and the same is true for length scales. However, it turns out that there exists a time interval which is an invariant, which means there exists a frame in which if you measure the time, that particular time is an invariant time. And what is that? The proper time. Why is it an invariant? So you have two events and you are measuring the time interval between these two events in a certain frame. Right? And you go to another frame, the same two events would be, the time interval would be different, right? Go from one frame to another, they would be different. Right? However, if I want to really say something about the time, real time interval between these two events, we should always be referring to the proper time, which is what? It's the time interval measured in a frame with respect to which the two particles are not moving. So it's like the two events have no physical displacement. So dx is 0 between these two events. So if I have two events, say A and B, and this is the dx and dt are the differences in time and space between them, we know that ds square equals to dt square minus dx square. Let's consider it's just one dimensional. And then I say, let's measure the time in a frame where dx is 0. So if dx is 0, and I call this particular time a special kind of a time interval and just label it with tau. So it's a time measured in a frame where dx is 0, which means there is no spatial difference. And you can clearly see this is nothing but ds, which is, as we know, is an invariant. So that's why we should always talk in terms of proper times when we are comparing time intervals between various things. And of course, if you take any other time, any other reference frame, right, any other reference frame, so there of course the time interval won't be d tau, it will be some dt, and dt and d tau would be related. How would it be related? By a factor, which is the famous time dilation factor. So proper time is the shortest time that you can measure between two events. It's the shortest time interval. It's a time interval measured in a frame which is at rest. The particles are at rest with respect to that frame, and so therefore the time interval is the shortest. Now I shall make another statement which is absolutely different from this, which is the following. And this is very, very important. So now let's consider two events. So let's draw a space-time diagram. Do this. This is actually the starting point of a geometric understanding. So let's just see this is x and t. And you have say two events A and B. Alright? And let's assume that these two events are causally connected, which means B is like the future of some event A. Right? We can always assume that. So B is a causal, A is like in the causal history of B. Alright? So the fact that A and B have a causal connection means that between A and B there would be connecting world lines. Various possible histories between these two events. Alright, so each of these paths that I've drawn corresponds to a history of evolution between the events A and B, right? In space-time. Now what you can do is, we can look at this reference frame and you can look at various paths in space-time, various world lines, and calculate this quantity. Which is like the proper time interval between A and B. But this integral is over various histories. Try to understand, you will get different numbers for each of these paths, right? Of course. Different curves, different integrals, line integrals. The important thing is to notice we are not looking at, or we are not comparing between reference frames. We have one reference frame, and in that reference frame we are calculating proper time interval for various world lines. Alright? And here, the statement that is made is very, very crucial. Because of the pseudo-Euclidean nature of geometry in space-time, something very counterintuitive happens. If you look at the straight world line, which is this, the straight line joining A and B, and these are all curvilinear ones. If you calculate this d, I call it delta tau, this quantity would be the largest. This quantity would be the largest for the straight line joining A and B. Can you tell me why? No, so it just follows, so we can just look at it this way. So we can choose our reference frame and give it a little rotation to align this straight world line like this first. And then everything else would be, so I've just sort of given it a rotation so that this thing is aligned vertically. And then I have all these various other ones. Look at this one. So for this, what is this integral? The integral is very easy to do because we call it TA and TB, TB and TA. What is for this? What is this? Just TB minus TA. So for, I call this 1, it is just TB minus TA. Look at this one. This has a slight bent over here, right? Which means it has a dx. This did not have any dx at all in its entire history. This has a dx over here. It has dx everywhere, in fact. Each bit of dx, when you do this integral, will take away pieces from dt squared. That's the interval, right? And it comes as a quadratic dx squared. The sign will also not matter. So along the curve, when you integrate, it has to be less than what you would get for this, because it's taking away the minus sign in the spatial part is taking away something from the time part, and thereby as you get curvilinear, more and more curved, just get lesser and lesser. This has the maximum proper time. Right? So remember, we call this ds as like a distance, but this is clearly so different from the Euclidean distance, which we know is shortest for the straight line. Why is that shortest? Because then everything comes with a plus sign. So go away and away, it gets larger and larger, adding little bits. Is this clear? As in, well, we have defined something very, very mathematical. So this dt square minus dx square as an interval itself is a mathematical object. I mean, that itself, to call it anything physical is actually, I don't know if that can be done, because ds is really nothing physical. Because there is no. But we have started with the definition of ds square as something minus something, because it's an invariant. But that itself does not really have a physical. We'll come to the physical signature importance of ds just shortly. Just give me that a little time. The physical significance is now can be stated actually in the reverse engineering way. So now I say that the straight world line is one for which the integral of ds, which is nothing but d tau, but the same thing as we saw, is a maximum. Or rather, we can just put a minus sign and then say that this quantity is a minimum. So we have a new definition of a straight line in space-time. If we have a space-time, we are now defining a straight line in that space-time, or a straight world line in the straight line, by saying that it's a geometric idea. Just like we have a straight line defined as the shortest distance between 2 points in Euclidean space, it is now defined as the shortest dish in space-time. Where ds is of course not the Euclidean distance, it's some strange mathematical object. And we can always put some constant, right, to make dimensions fine, and we can associate this. Now, what does this look like? I mean, where have you come across such principles in mechanics? Right. So you already know that the entire mechanics is formulated in the Lagrangian mechanics by a variational principle where you have an action which is minimum, rather which is stationary. You should not say minimum. It's stationary for the actual classical path. What does this word stationary mean? It means that you calculate this object for your true trajectory. And why am I calling it true trajectory? By the way, why are these not true and why am I saying this is true? Because we are doing special relativity, and if you believe there is no force, you would believe that the particle should just move in straight line. There are no force fields right here. So it's absolutely force-free, free particle. There's nothing there to change its direction or change it anywhere. So these are unphysical ones. This is the real classical solution. And this solution comes out as a solution to this variational problem, which means that you calculate this object for various paths. You will get a set of numbers around the actual classical path. You would see the variation of this is going to be 0. That's what it means, right? The first derivative is 0. Delta of this is 0. So we formulate this. We can formulate it in this form. Delta of ds equals to 0. Alright, but let's just go back one more slide and do a little exercise now. So we have established that in special relativity, this is a very good example, that we have established that in special relativity, the dynamics of a particle can be expressed through a variational principle of this form. So what can you call this? You can call the action, this action. So this is the action of a free particle in special relativity, right? Whose minima or whose extrema will give you classical trajectories. This is a very interesting example. So we have just written down the Minkowski definition of the interval and made a slight change in our approach. Instead of restricting ourselves to just Galilean transformations, we are not allowing ourselves to make any arbitrary transformations. So say, for example, you want to see the thing by sitting in a merry-go-round. So gone into a rotating frame, which is clearly an accelerated frame. Right? So when you go to an accelerated frame or rotating frame, let's assume that this frame is rotating with an angular velocity omega, and you make these transformations. So instead of the theta is now just capital omega t, you make this transformation, and lo and behold, what turns out is that your metric, your ds squared, now completely loses its Minkowski form. You can see a few things that has happened. First of all, the coefficient of dt squared, dx squared, dy squared, all of them, they have picked up picked up functions as their coefficients. And these are basically functions of the spatial coordinates and time. And also you have a cross term between dx and dt. So all you have to do is you have to just make a coordinate transformation and evaluate the metric. So the moment you jump into a non-inertial frame, you see that the form of the metric does not remain that simple. This is just an example. But you can generally say that when you just go over to non-inertial frames, in the general situation, your metric will pick up these strange terms, and you should basically be able to write, instead of eta, in a more general way, by introducing this g, which is now a function of coordinates. This is also true if you make a coordinate transformation from your Cartesian coordinates to non-Cartesian coordinates, right? You just go to spherical polar. You'll get an r square sine theta and all these various functions coming up, right? So Einstein actually saw that there's some connection between going over to curvilinear coordinates and writing the Euclidean or the Minkowski metric in non-inertial coordinate systems. There must be some connections between curvilinearity and non-inertial frames. And in fact, there was this famous equivalence principle. Anybody knows what the equivalence principle is? So basically, you can always, yeah. Right. So now you can make these maps. You can connect different things, right? You see that curvilinear coordinates, curvilinear metric which has a general curvilinear form, that in some way is simulating non-inertial frames. And non-inertial frames, in some sense, is related to gravity. So you can immediately have a feel that gravity probably has a connection with curvilinearity. Right? Just very heuristic, I mean, but it's an idea, right? So you immediately say there's a connection. There's one more way of looking at it in the opposite direction, so let me do that. So for that, we would need this action. So this action is given by this S. What would that alpha be? Can anybody tell? Can anybody make a guess what that alpha should be, that constant alpha that I put? Why would it be MC? Where do you get that MC? It is actually given by minus MC integral ds. Actually, this is representing a free particle, right? You can take this as alpha and you can do a Taylor expansion of the ds. And in the small velocity or infinite c regime, you should get back half mv squared. So that's your Lagrangian, you should be getting this as integral half mv squared dt in limit c tends to infinity. You should get this. And if you take this limit correctly, it turns out that this alpha, which is sitting here, has to be mc. This is two steps. So what you have to do is you have to write this as minus mc integral c dt root 1 minus v square by c square, and then do a Taylor expansion of this, right? A binomial expansion. And this, in the limit c tends to infinity, you will throw away all terms higher than v square by c square. What you will get, the first term will be a constant, by the way. When you expand this, the first term will be a constant. So what will that give you? So if you actually take this limit, you will get this as minus mc square and your 1 minus half v square by c square. Right? Ignoring all the half terms. dt. So this you can call the Lagrangian, of course, LDT interaction, and you have minus mc square plus half mv square. So this maps to your non-relativistic kinetic energy. This is a constant which you can throw away. But we won't throw it away, we'll keep it. What I shall do now is say that this is a free particle, and in the Newtonian scheme, how do I put in gravity? We put in a potential, a gravitational potential, right? So what you do is you add to your kinetic energy piece a potential energy term, right? Minus m phi, where phi is some potential. So let's do that and just put a minus m phi to this to say that there is some gravity, heuristically. The moment you do that and then try to go back here, because you want to finally write it as a change in ds. Let's see if we can do that. So if I call this the Lagrangian, with the m phi sitting here where phi is some gravitational potential, your action will be this times a dt and an integral is your action. And writing v as dx dt, and just simplify this and you will see that this action is again minus alpha minus mc integral ds, but now you can write this, but this ds now is changed. This ds square actually is now 1 plus 2 phi. It's 2 lines. What I have done is I have written down the non-relativistic Lagrangian half mv square. This is the relativistic piece which comes, and added an m phi to take care of gravity and translated it back to the metric and see that phi appears in the coefficient of dt square. Quite amazing. So gravity, if you say that this has the input of gravity, what it is doing, that it's manifesting itself as a change in the form of the metric. It's appearing as a function in the metric coefficient. So in all these approaches, what the final idea is that, in the general case, so there are 2 approaches. One, we started by looking at coordinate transformations, going into curvilinear coordinate system. There we saw that the metric picks up coefficients and cross terms probably. Then we saw that if you go to non-inertial frames, similar thing happens. And then we saw that if you incorporate gravity through this, in this prescription, again you see that the metric really picks up this general form. And this metric coefficient, the coefficient, the metric, this is the G00, right? This is clearly got to do with gravity in some sense. So this is justified to write this in the general form. All this is basically to justify writing the metric in this way. And then we say that ds could now be anything with a g mu nu, which can be any symmetric tensor. Why does it have to be symmetric? G mu nu has to be symmetric. Why does it?
Typically, the geometry can't change if you move in opposite direction. The geometry has to be same.
Okay. Any other reason? Well, of course, mathematically you can see it has to be symmetric. So if you have a contraction of any tensor between 2 tensors, one of which is symmetric and one of which is antisymmetric, what does the contraction give you? 0. And then any tensor can be broken into a symmetric part and an antisymmetric part. So see the x nu dot, those are clearly symmetric in the indices mu nu, right? So g mu nu cannot have an antisymmetric part. That if it was, it would just contract to 0. Okay. So I've written it this way by introducing a dot, is basically to give it the form of the Lagrangian, because we wanted to write it as something d something. And this lambda is a parameter that changes along the curve, along the geodesic. So what I'm saying is now that g mu nu could be any function, any symmetric tensor, and this expression that the variation of the integral of interval 0, this is going to still give you the, what would this give you? What was this in special relativity? What was this giving? It was giving the straight world line, right, for a free particle. But now this is the straightest possible, or what we can call it the new definition of the straight line when g mu nu is general. It's not Euclidean, or it's not Minkowski. So we have just generalized. We are saying that now this is the definition of the straight line, and we call it the geodesic when g mu nu is arbitrary instead of eta mu nu, which is a very specific case. So now we have the space-time whose geometry is now completely dictated by g mu nu. So to measure distance between 2 points, interval between 2 points, we need this function g mu nu. And the trajectory of test particles in this space-time is also completely specified by g mu nu because you have the Lagrangian, and you can find the Lagrange's equations of motion, which will only depend on g mu nu, right? Nothing else. So it has a complete description. And we write down the corresponding equations of motion. These are the Lagrange's equations of motion in this way, where we have introduced a symbol gamma given by this. It just follows. 2 pages of calculation, but it trivially follows. Okay, you just have to write the Lagrange's equation starting from that Lagrangian. Alright? These gammas are not tensorial objects because they have very strange transformations. But they are related to the first derivative. The important thing to note is that they are related to the first derivatives of the metric. So they are basically related to the first term in the expansion of the metric in a Taylor series. That's where the gammas appear. Alright. So we understand how to calculate geodesics if we know g mu nu. But who will give me the g mu nu? So we first say that the effect of gravity would be to modify your metric from its eta form to g mu nu. But how, we don't know. How do we get g mu nu? We don't know. But we know at least if I give you the g mu nu, we can calculate the action and we can calculate the geodesics. That part is pretty simple. So you can just find out these gammas and solve this differential equation and get a set of equations x alpha of tau. Tau is a parameter.
The question is relevant and what is metric here?
What is what? The metric. No, so yeah, in this particular situation, we're assuming that the metric is given to you.
No, that is fine, sir. I am actually what does it mean?
It tells you how the events on that space-time are connected. How the events are connected geometrically. So that is the most beautiful aspect of general relativity, that you have a continuum of points, and these continuum points are connected by a distance measure. This distance measure is the metric. The metric is something which is on the manifold, which tells you how you can go from one place to another, and you can calculate distances between these 2 points. I'll just tell you another way of putting this structure, which is as follows. So instead of looking at this picture of going from one point to another through an integral of the arc length, we can ask a slightly different question. We are asking now a question that, of course, space-time is not just points, it has fields on it, right? And we might want to move these fields around, and we might want to do calculus with these fields. For example, differentiate, integrate to various things of the fields. So let's assume that we have a vector field. Almost done? 1 hour is left? Oh, great. Okay, so the first approach that we took is that we start with a space-time with a given metric which allows you to calculate distances, right? And the geodesics are understood as through a variational principle. It's like an extremum principle. Now we ask a slightly different question. Let's assume that again we have the same space-time and we have the points which are labeled, which are labeling the events, and we have, say, a vector field. And we are probably interested in taking derivatives of this vector field or doing something with the vector field. So how do we do this? So Let me summarize basically what we have done, and then we can go into this. So we started with points, which are labeling various events, and we put on this set of points what is called a metric, which is a rule of calculating distances. This, from physical reasons, we expect should be related to gravitational field. We also expect that this has to probably be different from the eta the moment we go into non-inertial frames, and thereby the equivalence principle. Once we know this, we can calculate this, and these are the geodesics. Right? Now, let's do another thing. Let's say that we have the same set of points, x mu, which is defining my space-time. And now on this space-time, so let's assume that this is my space-time, a part of the space-time at least. And we have vector field. We have, what is a field?
Field is a function which assigns a number to every point in a space.
Doesn't have to be a number.
Quantity to every point in space.
It could be 36 numbers to a point. It's an object which is of course dependent on from point to point, right? So for example, if it's a tensor field, then one number won't suffice. So in 3 dimensions of space, a vector field would require 3 numbers at each point, right? So we are looking at 4-dimensional space-time, and not going into string theory where, I don't know, how many dimensions? 4 here. We are restricting ourselves to 4. This mu goes up to 4. 1, 2, 3, 4. Or 0, 1, 2, 3. And so I'm drawing this as an arrow, but I'm also saying these are 4 numbers. So what am I doing here?
Projecting it to.
Well, let's then not talk about this projection, because that would require us to form little frames over there, right? But let's not do that. Let's think of these arrows. Let's think of this vector field as porcupine's back, little arrows pointing. So it's like something like little arrows, and we go back to our old definition of vector, like a magnitude and a direction. So the arrow size and the arrow direction measures has the entire information about the vector. And these arrows are pointing in various directions, and they form a field. And we call this field A. I put this arrow, but this is in 4 dimensions. And I have to put x, because it's changing from point to point. A typical example would be an electric field. Okay. Now we are interested in differentiating this. So see, we have this, right? But we want to compare between points. Why? Because physical laws at the end of the day are always expressed in terms of tensor equations. Right? Why? Tell me, why are all physical laws, starting from your Newton's law to your Maxwell's equations, are finally laws which has to be expressed in terms of nothing but tensors of various ranks? Yes, because of an idea of what is called covariance. There are 2 ideas. One is the idea of invariance, and one is the idea of covariance. What is the idea of invariance? The number doesn't change. For example, ds squared is an invariant under a certain set of transformations. So when you have this idea of covariance and invariance, you have to first say under what transformation we are talking about. Clearly, something can be invariant with respect to a certain set of transformations, might not be an invariant with respect to some certain other transformation. Covariance is slightly different. What do you mean by covariance? So we talk about equations which are covariant, or expressions which are covariant. Right, which means you don't, for example, Newton's law has a certain form. Right? It's a derivative and there's a force. Now you don't want to go to another frame of reference where a certain new factor just pops up. Right? So the equations have to be written in a way, and why do the equations have to be written in that way? which is what? Which is the first principle of relativity. That your laws of physics should be the same in all reference frames. You cannot have Maxwell's equations, which has a certain number of terms in a certain frame, and you just go to some other frame and you have a new feature coming up, which is a frame artifact. Right? So that would break the covariance. So we don't want that. So what happens when you write things in terms of tensors? Why is it guaranteed that covariance will be ensured? If you write equations in terms of tensors, what are tensors? Right. So for example, let me say that I have an equation. Probably this is the equation of, grand unified theory. Equation of everything, and you have some tensor T, and you have ... mu, nu, rho, and you have something alpha, beta, gamma equals to some. Well, that becomes not equal to. So equal to some other tensor mu, nu, rho. This is a typical physical law, right? Can you think of a physical law which cannot be written in this form? Then probably that law has to be made covariant, relativistically not good. So if you come across a law of physics which cannot be written in that way, you have a chance to write a paper, to write a covariant form of that law.
This just means P equals to R.
Well, finally something is equal to something, right? Left hand side equals to right hand side.
That means we are actually comparing two aspects of some same.
Right, so the thing is, so long as these indices are matching, which means component-wise they are matching, what it essentially means is that you can do whatever transformation on this side, the same transformations would be affected on this side, right?
So the actual components change, but the equality doesn't change.
Right. So the fact that this equality is between something on this side and something on this side does not necessarily mean that these numbers will not change when you go from frame to frame. This is probably not an invariant, but this equation is written in a covariant manner. When would this be an invariant as well as a covariant equation? If this, for example, was just mass, a scalar. So that would mean it's an invariant as well. That number is not changing at all when you go from frame to frame. But in general, so say laws of thermodynamics, for example, many invariants, right? Scalars. Maxwell's equations, highly tensorial, so thereby you have to deal with covariance there. Okay. So that's why. So finally, we deal with, and when you talk about fields, tensor fields, you not only have the fields, but you have analysis, which means you have derivatives of those fields, right? Maxwell's equations involve derivatives of the electric and magnetic field. Fluid equations involve derivatives of fields, right? So you clearly have to do differentiation because physical laws manifest themselves. I mean, Newton discovered calculus because he had to describe physical laws. So physical laws manifest themselves in the language of calculus. That's how nature is. So you have to do analysis or calculus, differential calculus. So what is the first step of doing differential calculus? You compare neighboring points, differentials. What have we been doing over here? We have been still considering neighboring points and finding this ds, which is an infinitesimal, the first order. But the principle that we are applying over here is applying to an integral and functional. We are looking at an integral object, right? Integrated over the path, summing over individual cases, right? This is a different situation. For example, if we have as I said, a vector field, we can generalize it to any tensor field. We'll do that shortly. But let's say there's a tensor field and we want to take the derivative of this field. How do we do this? The field is changing from, the tensor is changing from point to point. So clearly you can have a gradient of that, right? For example, you want to take the gradient or the divergence or the curl, whatever, of this particular field. How would you do that? Hmm?
You just compare in every point with respect to the parameters.
No, we are looking at gradient, so we are looking at curl. So what is changing is the space, right? X mu. So first you have to. So this is very important. You are interested in not in discrete points, but points which are connected by what is called a differential structure. This is what is called a metric structure, which allows you to calculate distances. So when you say that my space-time has a metric structure, it means you have a g mu nu, which allows you to calculate distance between points. That doesn't guarantee that you can calculate derivatives. Actually, it does. If you have this, you can always define a limit, but it's not vice versa. You can probably define a derivative without having a metric structure. That's possible. So how do I compare two neighboring points? So you take the vector field, say a component, at some x, some x alpha, and the law of, the first principle of differential calculus, you take x plus delta x minus mu x alpha by delta x alpha limit to 0, right? Is that's simple, right? All you have to do is just to take the difference, the vector at two different near points. But you just go back to your high school vector analysis again. I give you two vectors and I ask you to find the difference. Here is my coordinate system. Say it's all flat, it's just your piece of paper. Here is one vector and here is another vector. Ask you to find the difference between these vectors. How would you do? You cannot but do that until you are comparing them at the same point. And then you apply the law of parallelogram. Simple, right? Two-step algorithm. You bring this to the same point, flip it, add it. That's the difference, right? This bringing it to the same point, translating it, it's done almost so intuitively and so without thought that we don't even care as to how important that could be. In bringing this is a vector field. This is the actual vector over here. What I need to bring over here is its parallelly transported version and then compare. Right? You cannot but compare without doing that. If your piece of paper is flat, you can just translate trivially. And thereby, the non-triviality occurs when you have a situation like this. So you start from the point P along the equator, a set of vectors. Here they are moving parallelly as you go towards Q, right? You're transporting them parallelly from Q to R. They're still parallel to their last step. R to P you see, they're still parallel. R is the north, somewhere near the North Pole. When it finally reaches P back, they have an angle in between them. You see what is happening. Clearly on flat, you will never expect that. You just go back. Go and come back, it will still remain parallel, right? But imagine this blackboard was something like the surface of a sphere, and you have been told to look at your last step and just maintain parallelism with the last one. And you see, this is what we'll end up with. So, if the underlying space, now we have an intuitive notion of what is called curvature. So, what is the difference between this flat blackboard and the surface of a football is the fact that the blackboard is flat and the sphere isn't. And what you do when you parallel transport a vector field, a vector in a closed loop on a surface of a sphere, you don't end up in coming to the same point. Which means this act of transporting parallel to itself, that has to be done in a very careful manner when you are working with space-times which are curved. And what would it depend on? It would depend on the geometry, right? What else can it depend on? The fact that this goes around and comes back without any change on flat essentially indicates that the geometry has nothing non-trivial about it. It's flat. However, if there were non-trivialities like that, you have to incorporate that, and the only thing that it would depend upon is some quantifier of the geometry of that underlying space, right? Agreed or not? So if we forget this part for the time being and just take this to be the premise that we are working in, so, and this is what we want to really compute, the derivative of a vector field, we have to first do this step. So now I say that the vector, when it parallelly transports itself from one point to another on a non-trivial geometry, it is most likely that it will change. When will it not change? If it's flat. But in the general case, it will change. And the change will depend on what factors? It will change, of course, on the geometry. Depending on what is there, on what are the features of the space-time, it will depend on that. It will also depend on how much we are going, how far we are going away. Further we go away, there's a greater chance of it getting more and more deviated from where we were.
So in case of flat space, when we parallel transport the vector, we find that when these two vectors are parallel, that means direction is maintained. But in case of curved space,
We are still doing that.
Yeah. How do we define this to be parallel? The same direction or something what?
Yeah, as simple as that. You just look at what your last arrow was. It does not have magnetic hysteresis, it does not remember the point P, it just knows that he is following the same direction. It's just doing what it has been told, just go in that direction. The arrow is not changing its direction. There are more strange attributes to this actually. In fact, we have drawn a triangle over here, you can see. 3 lines, right? But if you think of, in this picture not quite, but you can clearly see the 3 angles don't sum up to what you would expect in flat space. Much larger than that. In fact, you could have all 3 of the angles to be 90 degrees. If you take the equator and the two longitudes as the 3 sides of the triangle, you would have 90, 90 and 90. All 3 angles 90 degrees, right? So it's like 270 degrees as the sum of interior angles. So there are all these non-trivial issues when you go to curved space. Okay, coming back to this. So we have now a point where you have a vector, and there is another neighboring point where you have the vector. And now I've drawn this deliberately different, right? But this difference could be because of 2 things. First, of course, it's going to be different because it's a field. There's a natural difference, right? These are 2 distinct points. So the vector field is different at these 2 points. But there is also a difference which owes its origin. So if I just could bring this here, so it won't be something like this. So even if the field were completely homogeneous, which means if the vectors were really pointing all in the same direction, as a field, just by parallelly transporting from one point to another, you probably would get a non-coincidence, right? So there are 2 parts to it. One is because of pure geometric reasons, and one is the field itself. And basically, you have to consider both of this when you take this difference, right? So that brings us to what is called the covariant derivative, as you know. So this expression delta mu, so mu is the vector field under consideration, a component of that. And see, we have introduced the same gamma. Now, quite funny, we got this gamma before in our geodesics, right? And there we had not even talked about differentiation of vector fields or anything as such. We had our metric tensor, G mu nu, and we had established this, and then we got in the geodesic equations and we introduced these gammas as a symbol over there. Now I am using the same symbol again to do something else. that would require a lot of matching somewhere, right? I'm saying that the change in the vector field delta mu, which occurs just by virtue of parallel transport by dx alpha, is basically given by that expression. That minus sign is just for convention. It's just how it's basically used to match the two definitions. So then if you can just basically see that this total derivative or the covariant derivative of the vector will be your ordinary derivative plus a piece which now has the gamma. So this gamma, which has the information about your space-time, the geometry of the space-time, appears in the derivative in this manner. This is called the covariant derivative. Important thing to note is, as I said, is that we are using the same gamma symbol over here as a parameter which measures how much does a vector field deviate due to parallel transport. Right? So this way of introducing gamma is like taking a differential approach. Gamma appears here as a quantifier of the differential structure, right? So the gamma which appears here and the gamma which appears here, if we want them to be the same, which would be very good, because then we wouldn't need, because the gamma which appeared here were the first derivatives of the g mu nu, if you remember. Just go back to that slide. This was the expression for the gammas. Here it appeared as the derivatives of the g mu nu's, and clearly they have the information of the geometry, right? If this same gamma, which appears in the geodesic equation, could also be the same as this, then actually it can be shown, well, this is just what I stated, that the covariant derivative of the metric tensor itself must vanish. This is a very important statement. What I'm basically saying is, we have gotten the geodesic equations from two different points of view. What is the first point of view? The first point of view is an extremal principle. What is the second? Well, I have not discussed it, let me just do it and it will be clear what this means. The geodesic equations can be brought from this way of defining the parallel transport of a vector 2. Think about another definition of a straight line instead of being the shortest distance. What is the other definition of straight line you have got?
Move back.
Yeah, so a curve such that the tangent to it, right, as you go along, does not change direction. That's a straight line, right? And we just saw that we know how to transport a vector. Now let's take this vector as a tangent to the curve. And now if I say that this tangent does not change direction, which means that its covariant derivative along itself, along its own direction, is 0, then that should also give you the geodesic equations, right? The same. It's again the same definition of straight line. So let's see if we can do that. So we are saying that there's a curve and there's a tangent which I called u mu. And how I define this u mu? This is basically the tangent, so it's dx mu by d lambda, where d lambda is some parameter that changes along the curve. And then I'm making this statement that u alpha, u mu semicolon alpha. What does this mean? This is the covariant derivative of the tangent vector in some direction, and I make a dot product with itself, which means along the direction of the tangent itself, and then I say that this is 0, which means this doesn't change. Right? So we can just expand this out. We know the definition of the covariant vector derivative, and we know the definition of u mu. So let's just expand this out, and what we shall see. So u mu is dx mu d lambda, and what is this quantity? Let's just go back to the formula. You can maybe So it is del u mu del x alpha plus gamma mu alpha beta. Then you have u beta, right, equals to 0. This you can use the chain rule, right, and put u mu as dx mu d lambda. This will just become d2x mu d lambda square plus gamma mu alpha beta dx mu a mistake somewhere. This alpha.
dx alpha.
Sorry. dx alpha d lambda dx beta lambda. Exactly same equation, right? But see, this gamma appears here from this definition of parallel transport, right? To match these two definitions, it can be shown, it's just a very simple calculation, that it can actually work when the covariant derivative of G mu nu itself is 0. Okay? And this is what is said is a statement of metric connection compatibility. So there is a metric connection, and this is what is called an affine connection on the same manifold, on the same geometry. This gives a differential structure, and they are compatible through this. How do I define the covariant derivative of any arbitrary tensor? Can be generalized, right? So if I have any tensor, say t, mu, nu, rho, sigma, and I want to do a covariant derivative with respect to, say, alpha, can you tell me what this would be? You have to have the first term will of course be an ordinary derivative, and then for each of the indices you would have a gamma piece, right? And you have to choose the sign also properly, because the upper index and the lower index has a slightly different symbol sign for the gamma. So I just write this down. So this would be t, mu, nu, rho, sigma, comma, alpha. And first let's do these upper two. Right? So these are, everything else remains the same, right? So it's like gamma, mu. Then you can just take a nu, rho. What t shall we have over here? Nu, or I should not use nu. I should call, this is the problem, so I can take beta. So actually let me do 1, 2, 3, 4, that's the best thing. Okay. Alpha 1, alpha 2, beta 1, beta 2. Hold on. Easier. This will be just t, alpha 1, alpha 2, beta 1, beta 2, comma mu, plus gamma. And here I have to put something else. I call it alpha 1, alpha 1, alpha 2, alpha 1, alpha 2, some beta. That means this will have a t. What should I use? I'm running out of symbols. Rho, sigma, rho, rho, and alpha 2 remains, beta 1, beta 2, mu. Right? And then you would have one more term for alpha 2, so this one, and then minus a piece for beta 1, minus a piece for beta 2 to see the indices. So just index by index, just one index at a time, keeping the others unchanged. Okay. Laws of mechanics are expressed, as I said, in tensor equations which involves derivatives. And now, if these equations have to be covariant generally under transformations, you would have to now, instead of using ordinary derivatives, always have to use the covariant derivative. That's the main thing. So instead of using del mu, you have to use del mu as gamma. That's the main thing, because this is what takes care of the underlying geometry. So if you want to write down your equations of physics, equations of mechanics, in terms of derivatives, and you want them to be covariant under general coordinate transformations, then at least you have to make this substitution. So this is usually called the covariant derivative. No, let's just go back to what I said, and I didn't say it with some firmness, but now I'm going to emphasize this point. Remember that just this eta becoming a g mu nu, which is what we had started with, it's eta going to some g, where this g is now various functions, right? It's not it might not even be diagonal, it can have cross of diagonal terms. The fact that this is happening, it's not necessarily because of gravity, not necessarily because of intrinsic curvature. It could just be a choice of coordinate system. For example, as we know that if you have, let's go back to your Euclidean space and say ds squared is dx squared plus dy squared plus dz squared. I don't call it ds, let's call it dl. So here your metric is 1, 1, 1. Right? I can just go into this rho phi z, into the rho phi z coordinate system, and what would this look like? This would become d rho squared plus right? 1 r d theta and dz, right? So the fact that now there is a function here has got nothing to do with curvature or anything. We have just chosen a curvilinear coordinate system, right? We have just gone into a cylindrical coordinate system. This does not mean from going from x, y, z to this that we have actually done something non-trivial. The space is still flat. But see, the metric looks like as if it is not curved. It's curved, right? It looks, this thing, it looks like there is some curvilinearity. What it really means for space to be flat is that you can, by no coordinate transformation, had it been the case that no coordinate transformation would globally make this metric look like this. Had that been the case, then you would say, well, there's some real curvature to it. The statement that I'm making is that just by a coordinate transformation, I can always make a metric pick up strange pieces, right? But if there is a space-time, space, which by no coordinate transformation can be brought back to its Euclidean form globally, it means that clearly you cannot do it, right? Which means there has to be something intrinsically curved about it. So that is important. Artifact. Just going over to that coordinate system might make your space-time look like as if it is curvilinear. But there might not be intrinsic curvature. So how do I quantify something which is really curved or something which is really not curved? So we need a quantifier, something that I can measure and something which I can calculate and tell directly with, okay, fine, I just know this, and well, if it is 0 then it's flat, and if it's not 0 it's not flat. So we want something like that. So we just go back to this picture again, this picture. Now, as we stated, that the fact that when you took this vector field around a closed loop and you came back to the same point and it changed, this change owes to the fact that there's curvature, right? Somewhere it goes around a region where it has encountered curvature. Otherwise it wouldn't have happened. So the discrepancy that occurs to the vector, once you take it around a closed loop and bring it to the same point, should be a quantifier, a good quantifier as to the degree of curvature that's there. Right? And that's what we are trying to do. So we are saying that you parallel transport that vector field in a closed loop and then start shrinking this loop. By shrinking this loop, we are essentially finally doing a limiting process. We are finally coming to the center of the loop, and you have a tiny loop around it, and you see how much the vector changes when you go around it. If there is a change, then clearly that point has curvature, that center of that loop. So going around the loop and measuring the discrepancy is a measure of the curvature which is in the confined region of the loop. So now we can probably define a function which has values on every point, which measures the curvature by taking this limiting process of shrinking this loop size to 0.
Do you think of curvature at that point? Or
Yes.
did you say that, so you said curvature at that point, but you think about curvature in that small region space?
It is finally a limiting process
So curvature
at the point. So, so this is what we do. So we know how much a vector changes when you transport it by dx alpha, and now we take a loop integral. So this is around a closed loop, right? So we can just calculate this object. How do you think we can calculate? Basically, you have to do an integration by parts, right? Product of things. Integration of parts would bring in derivatives, right? And first function into integration of second and stuff like that. Right? So you would have definitely derivatives of gamma, which will appear here, right? You clearly see derivatives of gamma coming in. And what it turns out, and I'll just write down the expression, that this integral gamma mu nu alpha a nu dx alpha for a closed loop minus sign, this is proportional to, you'll get this basically just with suitable indices. A is the original vector field at the point, so it is at x. This is the little area of the loop, which is of course a second rank tensor because it's a cross product of two length elements. So this has one index, say nu, and say this is nu alpha. This will be and then finally this, what kind of object should this be? With index matching, it should have 4 indices, right? It has to have 3 indices which are here and 1 index over here. It's basically a 4th rank object. Because when you integrate this, you will have an area element which is a second rank tensor. Well, of course, this thing will come up, so this will be there. And then you will have a factor which will have all these indices. And that quantity, this is clearly geometric. area of the loop, which you are finally shrinking to 0, the size of this, and this is the vector field itself. This factor is what quantifies the effect of that entire bringing it around the loop. Basically what this is, you can, I mean, how will you do this? I mean, if I write in this form, probably it will be clear. Have you seen these kind of things in electromagnetism? What do you use? What theorem do you use? Make it a surface. Stokes. This is a line integral of something. It's a curl of that over a surface, right? And that surface is what comes around when you take the integral finally over the surface becomes very small. This is the area that comes out. That's also one way of looking at it. It's a curl of this dot ds. And when the loop is very small, you can throw away the integral and essentially consider that object to be same and not changing much. And then it's just proportional to the area of the loop, which is ds, delta s. Finally, this is what comes out. So, try to do this. It's a little involved. You have to just use a little bit of trick. And clearly you can see the derivatives of gamma come. Those are the curl factors. So you can see a curl-like object, right? Essentially the curl. It started with the fact that somebody has given us this G mu nu. Right? Somebody tells us what this G mu nu is for my space-time, and we have some heuristic belief that this G mu nu is probably related to gravity in some way. We don't know yet. What we studied today is essentially, given a metric connection on a space-time manifold, right? How we can differentiate, how we can find geodesics, and how we can quantify things like curvature. Right? The important thing is to note that this is not physics, this is just maths. Einstein made his contribution to this field. This was all done by Riemann and his disciples before Einstein, Riemannian geometry. If you have a metric, you can calculate geodesics. If you have the metric, you can calculate the gammas, you can calculate the curvature. All this is well understood now. So that is basically the description of general curved spacetime in 4D. Einstein had to relate this with the physics, and that we shall do in the next lecture. But before doing that, let me finish this discussion on the geometry. Few important analogies. First is look at these G mu nus. Remember when we used the potential phi to describe gravitational field, G00 had that 1 plus 2 phi factor. So these objects as a field, they are like something like the potentials that we have, right? And we shall see that these actually turn out to behave exactly like what we call the potentials in normal Newtonian gravity or even in electrodynamics. Potentials are not the good kind of objects to work with, as you know. Why? Because of they're useful, but there is always in electrodynamics. Why is it misleading sometimes working with potentials? And at constants, what is the actual word? What we have a freedom. Yeah, I heard that word. Yeah, so we have this gauge freedom. We can choose a certain gauge and add to the vector potential mu always a gradient, say. Because curl of A is the magnetic field, and that is of physical importance. Right? So you can always add constants, make some gauge transformations to your potentials. Next we come to this gamma, which are the derivatives of G, and finally the Riemann is derivatives of gamma. So basically this is second derivative of G. So if you make an analogy with electrodynamics, these objects, which are like the potentials, can in principle be gauged away by a suitable choice of coordinates. Like you could choose a gauge in which your scalar potential is 0. Electrodynamics, right? Choose a reference level somewhere. but that doesn't mean your electric field is 0. So that's a gradient of the potential. So here the important thing, the intrinsic quality of space, curvature, which is the derivative of the potentials, is of fundamental importance. You can probably gauge away gammas by a coordinate transformation by choosing some coordinates, but you cannot. If there is curvature, you can never gauge away curvature. So these coordinate transformations are in fact somewhat related. Not related, I would say they are analogous to gauge transformations that we have in electrodynamics. Alright? So the Riemann tensor quantifies the intrinsic curvature of space-time, and thereby the geometry of space-time, entire information of the geometry and its non-trivialness and its any difference that it has from flat space is contained in this function. And Einstein related curvature to gravity. So we shall come to that, and we shall see how we can actually relate curvature with gravity and with matter. So that is the second part. So let me give a little advertisement of what we shall be doing. So essentially what it turns out that Einstein gave an equation, namely Einstein's equation, which says that you have some contractions of this tensor, this Riemann tensor, which is related to something called the energy momentum tensor. Proshun wrote it today in the morning several times. So energy momentum tensor quantifies the matter distribution on the manifold, matter energy distribution on the manifold. And Einstein said that if there is a source of matter energy, that manifests itself as a geometry, which is this curvature, which essentially changes the space-time by curving it. The moment it curves it, you can solve the Einstein's equation, which involves this Riemann and the T mu nu, and get the metric. So if I give you the matter distribution of the space, you can use Einstein's equation, which relates the curvature with energy momentum, and you can find the metric. The solution to that would be these others. Like you have del square phi equals to, so you have a source which is matter, and the solution is the phi. And there's a del square. Very similar. Del square G is similar to R. So you will have the source, which is of the Einstein's equation, which will be now a second rank tensor, and you will have a second rank tensor over here, which is related to the second derivatives of the potentials, or in this case the metric. So the solutions will not be potential, but the metric. So what we finally get is that for a matter distribution, a certain geometric solution of the metric. Once you know the metric, your next step would be to calculate geodesics of test particles on that metric. So now we say that if there is a certain distribution of matter and you have a test particle. What is a test particle? What is the difference between a test particle and a source? Test particles are test particles in the sense that they don't disturb anything. They're just feelers, floaters. So they don't change anything. So they are so small that they don't really disturb anything. So a test particle will move or in a trajectory which would be the geodesics of the metric, and the metric would be the solutions to the Einstein's equation which relates curvature with the matter energy momentum. That is the prescription. So the next lecture I will do that part. We'll start with the energy momentum tensor, what that means, and then connect curvature, which is a pure geometric thing,